Welcome back to the AI Frontiers podcast. Today, we're diving into a groundbreaking research paper that tackles a major challenge in artificial intelligence: training massive language models. Joining me are Sam, the lead author of this paper, and Professor Chen, an expert in the field of deep learning. Sam, tell us about the challenge of training these behemoth models.
Thanks, Emily. These large language models are really pushing the boundaries of what's possible. We're seeing incredible gains in accuracy as models get larger, but training them becomes a huge hurdle. Imagine you have a model with billions or even trillions of parameters, and you need to fit it into the memory of your computer. It's like trying to squeeze an elephant into a shoebox. Current techniques like data parallelism and model parallelism simply aren't enough to handle this.
It's fascinating to see the rapid growth of AI models. It's like we're building ever larger and more complex machines, but we need new tools to make them work. Sam, how does your paper address these challenges?
That's where ZeRO comes in. ZeRO, which stands for Zero Redundancy Optimizer, is a novel approach to optimize memory usage during model training. We designed it to handle these massive models and train them efficiently. ZeRO has two key components: ZeRO-DP and ZeRO-R. ZeRO-DP focuses on reducing memory redundancy in data parallel training, and ZeRO-R tackles the remaining memory bottlenecks.
That's interesting. Can you elaborate on ZeRO-DP? How does it work?
Sure. Think of it like this. Imagine you're baking a giant cake, and you want to divide it equally among a group of people. Data parallelism is like giving each person a whole cake, which is wasteful and inefficient. Model parallelism is like slicing the cake vertically and giving each person a slice. ZeRO-DP takes a different approach. It divides the cake horizontally into thin layers and gives each person a layer. It's much more efficient in terms of memory. ZeRO-DP has three main stages: optimizer state partitioning, gradient partitioning, and parameter partitioning. In the first stage, we partition the optimizer states, which are used to update the model parameters. This significantly reduces memory requirements. Then we partition the gradients, which are calculated during the backward propagation. Finally, we partition the parameters themselves. This last step allows us to train models with almost any size, as long as we have enough GPUs to distribute the parameters across.
That's a great analogy. So by partitioning the model states, ZeRO-DP effectively shrinks the memory footprint of each GPU, allowing us to fit larger models into the same amount of hardware. Professor Chen, what's your perspective on this approach? Are there any trade-offs compared to traditional methods? Sam, that's a clever approach. However, I'm curious about the computational and communication efficiency. Doesn't partitioning the model states lead to more communication overhead? How do you maintain efficiency while reducing memory?
That's a great question. While it might seem like partitioning would cause more communication, ZeRO-DP actually minimizes the communication overhead. The first two stages, optimizer state partitioning and gradient partitioning, don't increase communication volume at all. The third stage, parameter partitioning, only increases communication volume by 1.5 times compared to the baseline data parallel approach. We achieve this efficiency by carefully scheduling communication to occur when it's absolutely necessary. We're not just blindly transferring data, we're strategically moving it only when it's needed for computation. It's like having a well-organized library where you only fetch the books you need, not the entire library. This way, we minimize data movement while maximizing efficiency.
That makes sense. So by reducing memory redundancy and optimizing communication, ZeRO-DP allows us to train much larger models without sacrificing performance. Sam, what are some of the key findings from your experiments?
Our experiments showed some very promising results. ZeRO can effectively train models with up to 170 billion parameters, which is 8 times larger than the largest models that could be trained efficiently using existing methods. We also observed superlinear scalability, which means that performance increases faster than the number of GPUs used. This is because ZeRO-DP allows us to fit larger batch sizes onto each GPU as we add more GPUs, leading to significant performance gains. Moreover, ZeRO is incredibly user-friendly. It's as easy to use as standard data parallelism, which means that researchers can now experiment with large models without needing to learn complex parallelization techniques. This is a big step towards democratizing large model training.
That's impressive. Professor Chen, how do you see these results impacting the future of AI research? Do you think ZeRO is a game changer?
Yes, I believe ZeRO has the potential to be a game changer. It's a significant breakthrough in system optimization for deep learning. It opens up new possibilities for developing and deploying even larger and more powerful AI models. This is especially important in areas like natural language processing, where larger models often lead to significant improvements in performance. However, it's important to remember that even with ZeRO, there are still computational power limitations to consider. Training a trillion parameter model would require enormous amounts of compute resources, which aren't readily available today. This highlights the need for future research in exascale computing and efficient training algorithms.
That's a crucial point, Professor Chen. Sam, what are some of the next steps in this research? What areas are you most interested in exploring further?
One of our main goals is to enable the training of trillion parameter models. We're currently working on extending ZeRO to support even larger models, and we're exploring new strategies for handling communication overhead as models get even bigger. We're also investigating the use of distributed optimizers, which could potentially further enhance the efficiency of large model training. Ultimately, we want to make it easier for researchers to push the boundaries of AI by providing them with the tools they need to train increasingly powerful models.
It sounds like there's a lot of exciting work ahead. Sam, Professor Chen, thank you so much for this fascinating discussion. It's clear that ZeRO represents a significant advance in large model training, and we're excited to see what the future holds in this area.
Thank you, Emily. It's been a pleasure.
Thank you for having me.